Okay, hello everyone. This is Chen. So I'm an incoming assistant professor at Brown University. I'm also a research scientist at Google. Today I'm going to talk about learning and using multimodal representations, specifically learning from videos. And we can learn a lot from videos, and we can build machine perception algorithms to do that as well. So this is a frame taken from the atomic visual actions dataset. And from this a single frame alone, we can build machine perception detectors or classifiers to recognize a lot of concepts. Examples include like for object detection, we can ask the algorithm to detect person, silverware on the plate, on the table, or food in the plate. We can also detect actions such as sitting, eating, and talking. And beyond those, we can also model the interactions among humans or like between like human objects, such as person holding a fork or eating food or talking to each others. And finally, we can do some short-term like temporal reasoning, such as predict what may happen in the next, like the male actor is likely to stand up. So since the era of deep learning, we have been like enjoying a lot of success on building those concept detectors, thanks to the availability of a huge amount of data, and also like we employ a lot of human annotations to annotate those concepts. And one question remains that as a human being, I can actually recognize much more from this single frame or from a short video clip beyond what's listed here. But not all of them are like easily to be defined or recognized by human annotators, and as a result, it's not easy to build supervised classifiers for those concepts. And examples for those concepts are like the relationship of the different actors, we may be interested in those. And some longer term temporal reasoning, such as like in the past, the food should be prepared by the parents. And some long future predictions, such as like after the meal, the dad is likely to do the wash the dishes, and we can go even longer and longer. And besides that, those concepts are more abstract and such, and as a result, harder to be annotated. Uh, their definition are also not only based on visual signals. It often depends on other modalities such as speech or like audio signals. And sometimes they even like require the understanding of some of the common sense knowledge, like people grow up and then they grow old. And how can we recognize those concepts from videos and benefit, harvest the common sense knowledge for other applications? So this is a topic I'm the most interested in. And the outline of this talk actually trying to focus on the multimodal aspect of video understanding. And in particular, I will cover the first topic, like multimodal learning objectives, the most. And after this, I will briefly discuss the architectures and the potential applications we have been developing for multimodal learning. And as we all know, like speech provides instructional knowledge, and this is especially true for a lot of instructional videos actually on the social media platforms such as YouTube and other video sharing platforms. For example, like for the cooking video, like as the uh, as the actor or YouTuber actually like do the demonstrate the cooking, they are also likely to explain what's going on. And that explanation is helpful for the machine learning algorithms to understand what's going on inside those visual frames. And the benefit is that although those videos are not explicitly labeled, there are a lot of them, such as maybe for on YouTube, there are more than 500 hours per minute uploaded. And the question becomes, how can we build machine intelligence algorithms to distill such useful information from those not labeled videos? And one exploration we did is with the so-called multimodal learning or like cross-modal dependencies. And given the visual frames of instructional video, and given the soundtrack of the same video and same timestamps, we can run automatic speech recognition system to extract the human speech information. But in the meantime, you're just kind of moving around your kickboard. That's temporarily aligned with the visual frames. And our goal is trying to learn the cross-modal dependencies automatically, such as we want to establish the correspondence between a kickboard or a cake with the middle frame and the action moving around with the middle frame as well. So that's we want to learn automatically. And besides the cross-modal dependencies, I also want to learn the temporal reasoning or temporal dynamics, such as how the object states from the first frame will be transformed into the future possible states. So AKA the temporal dependencies. So in 2 years ago, we realized that to learn both cross-modal and temporal dependencies, actually we can rely on the BERT or the multiple language modeling objective in order to establish such dependencies automatically in the data-driven manner and without any explicit human annotations. And due to the sake of time, I omit the details, such as how can I tokenize the visual frames into discrete tokens, but the details are discussed in detail in our paper. And our training objectives, given the corpus, our training objectives are very similar to those that of BERT. That is, we want to establish some of the cross-modal dependencies by masking out either tags, such that to fill in the blanks, the model needs to understand not only the language context, but also the visual context, like there's a cake in the middle frame and the action is moving around. So which both visual cues are helpful to understand, are helpful to fill in the blanks. And we can do the reverse, given the visual textual context, predict the missing visual frames. And we can also just do visual to visual prediction, which implicitly captures the temporal dynamics of video. And we train this video BERT model on around 300,000 YouTube cooking videos. And here's what emerged. So we first probed the video BERT model by explicitly testing out the cross-modal dependency by providing the model the text steps describing a recipe. And then we wanted to generate or to predict what's retrieved, what should be accompanying those sentences in the form of keyframes or short video clips. And we can see that although the appearances of those retrieved examples differs due to our quantization or tokenization process, the high-level semantics of those retrieved visual tokens are quite related to the text recipes. And we can also try to probe the model into understanding temporal dynamics by doing future prediction. And you can see that for a bowl of cocoa powder, the model is able to predict that it's likely to be put into an oven and then turn into either a brownie or cupcake. So again, the model is able to capture some of the meaningful, interesting temporal dynamics besides the cross-modal dependencies, which is nice. And we also try to get some of the quantitative numbers for this video BERT model. And what we did was the so-called zero-shot classification. Basically, we conditioned our model by providing the visual frames. And then what we do is that we provide a template sentence. Nowadays, people call it the probes. And we mask out the actions, namely the verbs and objects in a probing sentence, and then ask the model to fill in those actions and objects by itself. And here's what we found. So we measure the top 5 accuracy of action and object prediction in a zero-shot setting. And then we can see that as more and more, as the model sees more and more data, it's able to keep improving its classification accuracy. And what's even better is that our fully self-supervised and zero-shot recognition pipeline is able to even outperform the supervised baseline after seeing enough training data, which is promising. And I talk about this multiple masked language modeling objective for BERT and video BERT. And another potential objective for multimodal learning is actually contrastive learning. And contrastive learning has been studied a lot in the context of image representation learning. And the high-level idea is actually very simple. So you have a lot of images in the database. So you randomly take one image out from the data set, and then you try to do different random data augmentations to create the two views of the same data. And then you're trying to learn a widget encoder such that the two views, the encoded features of the two views of the same image are similar, and encoded representations of the two views of the different images are as different as possible. And this contrastive learning idea is not limited to be applied in the image representation learning domain. It has also been applied for cross-modal or multimodal learning. For example, in the MIL NCE paper, the authors explore trying to learn between the video frames and the speech transcriptions. And you can see a key difference with video BERT is that instead of they are trying to model the interactions at the token level or at the frame level, they are now treating the video frames as a completely sequence as view one, and the speech as another complete sequence in a different view, and then trying to do contrastive learning among the two. And for images, I think the most successful example is this CLIP model from OpenAI. It also does cross-modal contrastive learning, but tries to scale the training data to be a huge amount. And the results, the learned representations and the cross-modal correspondence are surprisingly good. So it's a lot of successful cases for contrastive learning, in particular for cross-modal cases. And the typical self-supervised learning or contrastive learning setup is that we have a pre-training set that is unlabeled, such as images and videos, and we do the contrastive learning objective. And during evaluation, we employ a small label data set, train a linear classifier, and do supervised learning to map the representations into discrete concept labels. This is the standard setup. And I just talk about different instances of contrastive learning, such as maybe between video frames and speech. And there are also other forms of contrastive learning in the sense that different views can be constructed, such as the different views among different timestamp, from frames at t and t+2. And also for images, the views can be constructed as luminance and chrominance. Or in the even earlier days for self-supervised learning, actually you can try to associate the different spatial crops or different patches of the same cat or same instance and trying to establish their correspondence in order to capture the high-level semantics of this cat or some other objects. The question I want to ask myself is that are there, given different ways to construct views or including the cross-model views, are there guiding principles on what makes good pairs of views? And this is a topic we studied in a new research paper last year. And so we start with some toy examples, such as image contrastive learning with varying patch distance. And we try to control the minimum distance between the two randomly selected patches with the intuition that the farther away the two patches are sampled from the same image, the less mutual information is shared between the two views. And we want to vary basically this shared information between two views and see how it impacts the classification accuracy for a downstream benchmark. And in the right figure, basically on the x-axis is the lower bound and the mutual information as we measure it using the NCE lower bound. And the y-axis is the classification accuracy on the STL10. And interestingly, we can see that the relationship is not monotonically decreasing or increasing. Actually, it forms a reverse V shape as the mutual information or the lower bound of the mutual information or the distance of the patches becomes bigger and the mutual information becomes lower. The downstream classification accuracy actually first increases and then start to decrease. And then we can try it on other manually designed data augmentations. And basically, we tried it on color jittering and also the random crop. And we observe a similar trend, which is the reverse V shape. And that's interesting. Like, what's the relationship between the mutual information shared between two views and the downstream classification accuracy? So to answer this question, we actually try to propose a simple hypothesis, which is the information minimization hypothesis. That is, the mutual information shared by views is desired to be task related. So we want to preserve a sweet spot, which is maybe the peak of the reverse V shape, is that trying to preserve as much mutual information that related to the downstream task as possible, but at the same time, reduce or remove other irrelevant information as much as possible. And in this interpretation, the reverse V-shaped curve can be seen as an empirical observation that the irrelevant noise seems to be removed first when we try to try to reduce the mutual information or its lower bound by strengthening the data augmentation. And we can see that at the beginning, when we try to reduce the mutual information, the noise are removed, and then empirically. And then as we further reduce the mutual information, the information related to the downstream task, like the semantic labels of the objects, are starting to getting removed, and then the downstream transfer learning performance starts to decrease. And then this is good, but we don't actually know how to where is the sweet spot, right? So we want to learn to generate views. And our solution is that we try to generate views that with an invertible view generator and trying to minimize the lower bound of the mutual information. And then we try to also preserve as much information in the representations as possible. So to learn the representations, we still use the standard contrastive learning, which optimize the lower bound of mutual information. But to preserve the information that is task relevant, our current solution is to make the pre-training semi-supervised by providing the downstream task information in terms of the labels when we try to generate the views. This is not ideal, but as we show hypothesis earlier, so it's unlikely that the optimal views of contrastive learning can be discovered automatically without knowing the downstream task first. And we show experimentally that once we try to learn our wheel generator, then most of the runs, they start to approach to the optimal sweet spot, which is the orange square shown in the middle. So like I mentioned, my take-home message is that wheel construction is important, but on the other hand, it's a task dependent. So one future direction will be trying to generate the wheels automatically and further reveal the secrets of how to construct the wheels for multimodal learning properly. And another thing that I'm interested in is actually just learning across time. Because when we're trying to learn across time, we are facing an issue that, for example, there is an orange and the sliced orange that they differ by delta t in the same video. And if we do the standard contrast learning, the natural wheels from between wheel one and wheel two are like motivated by our training objective to be invariant of the augmentations we apply. And sometimes such invariance is very desirable as studied by a lot of previous papers such as Sinclair, but sometimes such invariance hurts the performance, such as like if we want our model to capture the fine-grained temporal signals, then we don't want to learn the representation such as to map the two frames that are t seconds apart into the same point or nearby points in the latent space because the temporal information, or in this particular case, the shape deformation information is lost. And if we want to transfer our representation to some downstream task that requires fine-grained temporal reasoning, then there's no way to recover such information because it's already lost during the feature encoding stage. And there were like previous effort trying to fix this potential issue. One is that so we have like a lot of different data augmentations, but we can also do a lot of learn a lot of representations. Some of them are invariant to a certain data augmentation, but aware or do not care about the other data augmentations, such as so that the information related to certain data augmentations can be recovered from certain embeddings learned by this overall training objective. But the potential issue of this framework is that we first need to know the potential data transformations beforehand, and then we need to design projection ahead and the pre-training objective for each of those individual like data transformations we care about, so it may not scale well. And another task is that another solution is to learn equivariant representations. So instead of invariant, we want the representations to like transfer the way that we transfer the inputs, such as for self-driving is that trying to predict the visual features if we take a left or take a right, right? And however, the equivariant constraint is quite strong and it may not necessary for many tasks where all we only need to know is to let the representation to be aware of the transformations, not necessarily to be strict equivariant. So our solution is actually quite simple. So we want our representation to be aware of the data augmentations. So we simply encode those data augmentations and provide those as input to the projection head to the contrastive learning framework. And our hope is that for those transformations that are actually useful and then predictable, our training objective encouraged the model to actually try to learn a representation of the second wheel, which is the sliced orange, differently from the first wheel, which is the whole orange. But then by using the information that the temporal gap between the two wheels is t seconds, trying to map the learned representations of wheel two in the latent space to wheel one by employing like implicit temporal dynamics model to go back in time into the whole orange, and then trying to map the two latent representations to be close to each other. On the other hand, if the data augmentation information is hard to predict or is not deemed relevant by the training objective, then it has the freedom to ignore such encoded data augmentations. And in that case, it like basically becomes the standard contrasted learning objective. So it's a more unified and generalized framework than the standard contrasted learning framework objective. And then as a result, our hope is that by learning this implicit prediction model based on the temporal augmentations, and in this particular case, the temporal dynamics, we want our representations to like not only capture the shared information, such as the color, but also the predictable information, such as shape or other information related to visual dynamics and temporal dynamics. But the unpredictable things are still like noise and discarded, such as camera motion. So this is our goal, and here's our training objective. I'm not going to into details, but basically, compare with the standard contrasted learning, we not only construct the wheels, but we also provide the encoded data augmentations. And the data augmentations are composed by a transformer model so that instead of learning a separate projection head for each individual data augmentation of interest, we can actually compose them together with our projection head. And that's more scalable. And in our later experiment, we demonstrate its effectiveness. So in particular, because we focus on temporal dynamics, you pick a data set that's most aware or like salient of temporal dynamics, which is the something something data set. As you can see that here are the examples of the videos in something something. The classes are actually quite aware of the ordering of the frames, unlike many of the other data sets like maybe UCF or HMDB or kinetics. Those data sets, if you discard the temporal information and use backup frames, you may get a pretty decent accuracy for classification. But it has been shown that on this data set, if you throw away the temporal information, the performance will be much lower. And this is why we want to evaluate the performance on this data set. And here I'm showing the like linear classification evaluation using the setup that I mentioned earlier, the standard contrasted learning setup, where we do a self-supervised pre-training first, and then we freeze the representations and train the classifier on the target data sets. And we can see that there are a lot of numbers, but the take-home message is that if we encode the spatial crop information and the temporal shift information, then both of the encoding that helps the performance of the downstream classification task. And then we also applied on the like what to encode for the temporal shift. We can either do just the error of time, like the sign of the delta t, or we can provide the whole delta t. And we can see that if we provide the whole delta t, then the performance becomes better than like just the error of time itself, which means that the more information about time shift is desired to improve the downstream classification accuracy. And we also try to actually see what's being captured in those representations beyond just simple classification accuracy. We actually try to use the representation to predict the time shifts between randomly sampled clips and in some videos, and see if different representations is able to do this time offset prediction accurately or not. And somewhat surprisingly, because the gap is really big, but as we initially hypothesized, that if we do not encode time, the temporal information is basically discarded and it cannot be recovered. As a result, the time offset prediction accuracy is very low. But if we try to like preserve such information and provide as encoding during pre-training of the representations, the time offset is actually like much higher, the accuracy. So, which means that the temporal information is being encoded in those representations. And we also show that as we desired different data augmentations can be composed, and they are complementary to each other. And when we try to dig into the details of those spatial augmentations in the individual classes of this benchmark, we can see that for when we encode spatial cropping, those classes that benefit the most are those like trying to lift up something or like put down something from left to right, where this spatial localization is important. And similarly, if we dig into the classes that benefits the most with time encoding, is also where the error of time or the ordering of the frames matters the most. And we also made an attempt to handle very long videos. And by doing that, we actually try to like solve object state transition tasks, where we try to, given the initial state and target condition expressed either by tags or by some latent features, we want to anticipate the future object states, such as from raw egg to a boiled egg, but the difference is unknown in time. And then we try to discover key states based on visual dynamics. Due to the sake of time, I'm not going to go into details, but I'm going to show some of the visualizations. So our model basically trying to learn temporal and cross-model dynamics and trying to close the circles. So start from a certain modality. We try to first go to the other modality, which is speech in this case, and we predict forward in time. And then we try to like map to the other modality and go back in time and try to close the cycle. And we can start from either like visual information or the speech information as shown here. And then once we learn such a like temporal cross-model cycle consistency model, we are able to actually like try to do a lot of interesting tasks, such as using the learned temporal dynamics to unshuffling the image collections and order them by time. Or we can do future action anticipation, where we show our method outperforms a wide range of previous tasks with different objective in terms of future prediction. Okay, a quick recap. So I talk about multimodal learning objectives, BERT, which use the MLM objective for training, the composable augmentation encodings, which uses a modified contrastive learning objective. And then the last work, which I briefly talk about, uses temporal cycle consistencies. So in the remaining 2 minutes, I'm going to talk about architectures for multimodal learning. And for multimodal learning, a lot of our previous work when we do classification is actually trying to do late fusion. Like we build a separate visual encoder and the audio or speech encoder, and we try to combine the logics at the end and use that combined logics for classification. And the reason for doing that is that at the old days, there was not a unified architecture for encoding different modalities. And so as a result, it's typically beneficial to do like late fusion, because we can treat the two encoders as black boxes. And nowadays, transformers has been shown to be super effective for text, video, and audio signals. And can we do something better, like earlier fusion or like other formal fusion? So in our like work under submission, we basically try to understand how to fuse different modalities and how we want to exchange the information. Like we can either do a full attention using the self-attention mechanism by directly concatenating the tokens belonging to different modalities, such as the RGB frames or the audio spectrograms, and then we do a full self-attention to fuse everything. Or we can assume that the information relevant to the other modality is actually quite compressible, and then we only need to employ a bottleneck to compress the information from one modality and pass that on to the other modality. And the benefit of doing a bottleneck, first, it has fewer freedom, so less prone to overfitting. And then it also improves the model speed by lowering the flops. And we can see that here we basically show that by employing the attention bottlenecks, which in our case, we only use 4 tokens to exchange information between the different modalities, which is RGB and audio, we're able to outperform the vanilla across full self-attention by huge margins. So that's actually encouraging. But on the other hand, it also highlights an open question. That is, what would be a proper way to combine the information across different modalities? And is that mechanism like generic or task dependent? And I'm going to skip this due to the sake of time. But some of the interesting future works I'm interested in, like understanding long-form videos, such as movies, and capture the hierarchical video dynamics. And I also want to learn from huge amount of unlabeled videos the visual common sense and transfer them to other modalities, such as like language understanding, including some concepts like related to weights, size, speed, and color. And I also want to transfer to different tasks beyond just classification. And one example is actually we try to transfer our multimodal representations to visual navigation task for embodied agent, where we actually like try to improve the intermediate language representations as the interface between human and the agent, and also try to use a design architecture that captures the long-term temporal dependencies. Okay, thank you so much. And I'm happy to take questions online or like feel free to send me an email. Thank you. Bye.